Alright, so we're picking back up in our reading of Reversing for Everyone. I am skipping part 17 that speaks about installing Linux and VirtualBox. So we're going to start off at part 18, Vim Text Editor. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Now that we have a working version of Linux, we need a text editor that we can work with in the terminal. To begin, open your terminal and type cd into your home directory, and then vi.vimrc. This will open up the vi text editor. The first thing you need to type is the letter I to set the editor to insert mode, so you may begin typing. Now I'm going to type set number, set smart indent, set tab stop equals 4, set shift width equals 4, and set expand tab. After you are done typing, press the escape key and type :WQ and press enter. Congratulations, you created your first file. This is a one-time file that we need to create in order to use our text editor the way we want it to perform. The first line states set number, which means we would like each file to show line numbers, as this is essential for debugging code. The set smart indent, set tab stop, set shift width, and set expand tab statements set forth rules to properly format code and allow 4 spaces per tab indent, which will help our code to look clean. There are several commands you need to be aware of. Keep in mind, to go into command mode rather than insert mode, you must press the escape key. Below are the most common commands. J or down arrow to move the cursor down one line. K or up arrow to move the cursor up one line. H or left arrow to move the cursor left one character. L or right arrow to move the cursor right one character. 0 to move the cursor to the start of the current line. $sign to move the cursor to the end of the current line. B to move the cursor back to the beginning of the preceding word. DD deletes the line the cursor is on. Capital D deletes from the cursor position to the end of the line. YY copies the current line. P puts the copied text after the cursor. U to undo the last change to the file. And :W to save file. :WQ to save the file and exit the text editor. And :Q exclamation point to quit the text editor and to not save any changes. You will be consistently moving between command mode with the escape key and insert mode with the I key. Remember that when you want to insert characters, you need to be in insert mode, and when you want to move the cursor other than moving to the next line, you need to be in command mode. Now that we have VI configured, let's install Vim, which has some better functionality. Simply type sudo apt-get install Vim. Once that is installed, instead of using VI, we will now use Vim. I look forward to seeing you all next week when we talk about why it's important to learn assembly language. Part 19, Why Learn Assembly. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Why learn assembly language? Java is the most in-demand programming language and will get me a job immediately, so why in the hell would I ever waste my damn time learning this archaic assembly language crap? So many people ask me this question, and it is true, Java is hot and in the greatest demand, and there's nothing wrong with learning Java. However, the threats that face society more than anything in this world, above everything else, is the cybersecurity threat. With that said, Java offers a great career path, and I would encourage you to learn it. However, Java is not the only game in town. Most malware is written in higher level languages. However, most malware authors do not give the attackers their source code so they can properly deal with their crafted attack. The hackers use a multitude of high-level languages, and the demand for new professional malware analysts, reverse engineers, continue to grow daily. When we examine malware, more than not, we get only a compiled binary. The only thing we can do with a compiled binary is to break it down instruction by instruction in assembly language, as everything ultimately goes down to assembly language. When someone says assembly language is a dinosaur, I say to those people, let's have that conversation when your entire network is brought to its knees and you can't log into a single terminal or manipulate a single machine on your network. Let's talk about how useless assembly language is at that time. Understanding assembly language allows one to open a debugger on a running process. Each running program has a PID, to which is a numerical value which designates a running program. If we open a running process or any bit of malware with a professional or open source tool like GDB, we can see exactly what is going on and then grab the EIP instruction pointer to go where we need it to go to have complete control over program flow. Most malware is written, as I have stated, in a middle level language, and once compiled, it can be read by the hardware or OS as it is not human readable. In order for professional cybersecurity engineers to understand this, they must learn to read, write, and properly debug assembly. Assembly language is low level and has many more instructions than you would see in a higher level application. The prior 18 lessons in this tutorial series gave you the basics of x86 hardware. As I have stated in prior tutorials, we will focus on 32-bit assembly debugging, as most malware is going to try to affect as many systems as possible. And although there is 64-bit malware, 32-bit malware is significantly more destructive and dangerous and will be the focus of this series. I look forward to seeing you all next week when we learn the basics of instruction code handling. Part 20, Instruction Code Handling. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. A CPU reads instruction codes that are stored in memory, as each code set can contain one or more bytes of information that guide the processor to perform a very specific task. As each instruction code is read in from memory, any data needed for the instruction code is also stored and read into memory. Keep in mind, memory that contain instruction codes are no different than the bytes that contain the data used by the CPU, and special pointers are used to help the CPU keep track of where in memory data is and where instruction codes are stored. A data pointer helps the CPU keep track of where the data area in memory starts, which is the stack. When new data elements are placed in the stack pointer moves down in memory, and as data is read from the stack pointer moves up in memory. Please review Part 15, stack, if you don't understand this concept. The instruction pointer is used to help the CPU keep track of which instruction codes have already been processed and what code is to be processed next. Please review Part 12, instruction pointer register, if you don't understand this concept. Each and every instruction code must include an opcode that defines the basic function or task to be performed by the CPU, to which opcodes are between 1 and 3 bytes in length and uniquely defines the function that is performed. Let's examine a simple C program called test.c to get started. All we are doing is creating a main function of type integer to which it has a void parameter and returning 0. All this program does is simply exit the OS. Let's compile and run this program. Let's use the obj dump tool to find the main function within it. Here is a snippet of the results you would get by running the above command. Here are the contents of the main function. Keep in mind the below is Intel syntax as we spoke about in the last tutorial. On the far left we have the corresponding memory addresses. In the center we have the opcodes, and finally on the right we have the corresponding assembly language in Intel syntax. To keep this simple, let's examine memory address 80483DE, where we see opcodes B8 00000000. We can see that B8 opcode corresponds with the move EAX, 0x0 instruction on the right. The next series of 00000000 represents 4 bytes of the value 0. We see move EAX, 0x0, therefore the value of 0 is moved into EAX, therefore representing the above code. Keep in mind the IA32 platform uses what we call Little Indian notation, which means the lower value bytes appear first in order when reading right to left. I want to make sure you have this straight in your head, so let's pretend the value above was move EAX, 0x1. In this scenario, the corresponding opcode would be B8 01000000. If you are confused, it is okay. Remember Little Indian? Keep in mind EAX is 32 bits wide, therefore that is 4 bytes. 8 bits equals 1 byte. The values are listed in reverse order, therefore we see the above representation. I look forward to seeing you all next week when we dive into the details about how to compile a program. Part 21, How to Compile a Program. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's look again at last week's C program and take a deeper look at how we turn that source code into an executable file. To compile this program in C, we simply type gcc-m32-ggdb-o exit for the name of the output file, and exit.c is the name of the file containing our source code. This single step will create exit.o, which is the binary object file, and exit, which is the binary executable file. If we want to convert this C source code to assembly, we need to use the GNU compiler in the below fashion. Let's start by running the below command in the terminal. GCC dash capital S dash M32 dash capital O 0 exit.c. Let's begin with the dash capital S switch. The dash capital S switch will create comparable AT&T syntax assembly source code. The dash M32 will create a 32-bit executable, and the dash capital O0 will tell the compiler how much optimization to use when compiling the binary. That is the capital O and the numeric 0. Numeric 0 in that case means no optimization, which means it is at the most human-readable instruction set. If you were to substitute a 1, a 2, or a 3, the amount of optimization increases as the values go up. This step above creates exit.s, which is the equivalent assembly language source code as we mentioned above. We then need to compile the assembly source code into a binary object file, which will generate a exit.o file. GCC-M32-C exit.s-o exit.o. Finally, we need to use a linker to create the actual binary executable code from the binary object file, which will create an executable called exit. GCC-M32 exit.o-o exit. Last week, when we examined the executable file exit in a program called objdump and examined the main area, we saw the following below, except this time we will use AT&T assembly language syntax. obj dump -d exit, and we're piping that into grepping for main dot colon and dash capital A 11 for the 11 lines immediately after the string that we are grepping for, which is the main function. And this command will create the following output below. Let's examine the code in the debugger. Let's start GDB, which is the GNU debugger, and first list the source code by typing L, then set a breakpoint on main and run the program. Finally, we will disassemble and review the output below. In each of the three above examinations, you will essentially see the same set of instructions, which we will take a deeper look at as to what is exactly going on in future tutorials. Throughout this tutorial series thus far, we have been looking at Intel syntax assembly language. We are going to turn our focus to AT&T syntax, as I have stated above, as this is the natural syntax utilized in Linux with the GNU assembler and GNU debugger. The biggest difference you will see is that in AT&T syntax, the source and destinations are reversed. AT&T syntax looks like this: movl %, ESP, comma, %, EBP. This means move ESP into EBP. In Intel syntax, we have move ESP, comma, EBP. This means move EBP into ESP. You will also see some additional variances as AT&T uses additional variances, which we will cover in a later tutorial. If we wanted to create a pure assembly code program which does the same thing above, we would type what you see in the following section from 1 to line 14. To compile this, we would use the GAS assembler and linker. AS -- 32 GS tabs -O exit __ s dot O exit __ s dot s LD -M elf _ I386 -O exit __ s exit __ s dot O, and we can run exit. To run any executable in Linux, you type // and the name of the binary executable. In this case, we type // exit and press return. When we do so, nothing happens. That is good, as all we did was create a program that exited to the OS. I look forward to seeing you all next week when we dive into more assembly code. Part 22, ASM Program 1, Moving Immediate Data. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. I appreciate everyone being patient, as it has taken 21 lessons to get to our first ASM program. However, very necessary background had to be covered in order to fully understand where we begin when developing assembly language. We are going to create 32-bit assembly programs, as most malware is written in 32-bit mode in order to attack the maximum amount of systems possible. Keep in mind, even though most of us all have 64-bit operating systems, 32-bit programs can run on them. For the most part, we have been working with Intel syntax when it comes to assembly. However, I am going to focus on the native AT&T syntax going forward. It is very easy to convert back and forth between Intel and AT&T syntax, as I have demonstrated in prior tutorials. Every assembly language program is divided into 3 sections. You have the data section. This section is used for declaring initialized data or constants, as this data does not ever change at runtime. You can declare constant values, buffer sizes, file names, etc. The second section is the BSS section. This section is used for declaring uninitialized data or variables. And the third section is the text section. This section is used for the actual code sections, as it begins with a global _start, which tells the kernel where execution begins. Critical to any development is the use of comments. In the AT&T syntax, we use the pound symbol or the hashtag symbol to declare a comment, as any data after that symbol on a respective line will be ignored by the compiler. Keep in mind, assembly language statements are entered in one statement per line, as you do not have to enter the line with a semicolon like many other languages. The structure of a statement is as follows: label, mnemonic, operands, comment. A basic instruction has 2 parts, of which the first one is the name of the instruction, or the mnemonic, which is executed, and the second part is the operand or parameter of the command. Our first program will demonstrate how to move immediate data to a register and immediate data to memory. Let's open Vim and create a program called moving immediate data.s and type the following. To compile, you type AS-32-O, the name of the output file, which is going to be moving immediate data.o, followed by the name of the file we just created, which is moving immediate data.s. Then we run the command ld-m elf I386-O for the output file, which will be moving immediate data, and then the name of the file we created previously, which is moving immediate data.o. To run, you type /moving immediate data. I would like to show you what it would look like in Intel syntax as well. Before we examine this part, you will need to type sudo apt-get install NASM in a command prompt, which will install the netwide assembler. To compile, you type NASM-F ELF32 and the name of the file moving underscore immediate underscore data dot ASM. Then we type LD-M ELF underscore I386 -O followed by the name of the output file, which will be moving underscore immediate underscore data, and then the name of the file that we created running the previous command, which is moving underscore immediate underscore data dot O. To run, you type /moving underscore immediate underscore data. Oh, what the heck? There is no output. That is correct, and you did not do anything wrong. Many of our programs will not actually do anything, as they are not much more than sandbox programs that we will use in GDB for analysis and manipulation. Next week, we will dive into the GNU GDB debugger and see what is going on under the hood. I want to take some time and discuss the code at lines 20 to 22 in the AT&T version and the Intel syntax version as well. This set of instructions takes advantage of what we call a software interrupt. On line 20 in the AT&T syntax, we move L $1, %EAX, meaning we move the decimal value of 1 into EAX, which specifies the sys_exit call, which will properly terminate program execution back to Linux so that there is no segmentation fault. On line 21, we move $0, %EBX, which moves 0 into EBX to show that the program successfully executed. And finally, we see int $0x80. Line 20 and 21 set up the software interrupt, which we call on line 22 with the instruction int $0x80. Let's dive into this a little deeper. In Linux, there are two distinct areas of memory. At the very bottom of memory in any program execution, we have the kernel space, which is made up of the dispatcher section and the vector table. At the very top of memory in any program execution, we have the user space, which is made up of the stack, the heap, and finally your code, all of which can be illustrated in the below diagram. When we load the values as we demonstrated above and call int 0x80, the very next instruction's address in the user space, ASM code section, which is your code, is placed into the return address area in the stack. This is critical so that when int 0x80 does its work, it can properly know what instruction is to be carried out next to ensure proper and sequential program execution. Keep in mind, in modern versions of Linux, we are utilizing protected mode, which means you do not have access to the Linux kernel space. Everything under the long line that runs in the middle of the diagram above represents the Linux kernel space. The natural question is, why can't we access this? The answer is very simple. Linux will not allow your code to access operating system internals, as that would be very dangerous, as any malware could manipulate those components of the OS to track all sorts of things such as users, keystrokes, activities, and the like. In addition, modern Linux OS architecture changes the address of these key components constantly as new software is installed and removed, in addition to system patches and upgrades. This is the cornerstone of protected mode operating systems. The way that we have our code communicate with the Linux kernel is through the use of a kernel services call gate, which is a protected gateway between user space, where your program is running, and kernel space, which is implemented through the Linux software interrupt of 0x80. At the very, very bottom of memory, where segment 0, offset 0 exists, is a lookup table with 256 entries. Every entry is a memory address, including segment and offset portions, which comprise of 4 bytes per entry, as the first 1024 bytes are reserved for this table, and no other source code or no other code can be manipulated there. Each address is called an interrupt vector, which comprises the whole called the interrupt vector table, where every vector has a number from 0 to 255, to which vector 0 starts off occupying bytes 0 to 3. This continues with vector 1, which contains 4 to 7, etc. Keep in mind, none of these addresses are part of permanent memory. What is static is vector 0x80, which points to the services dispatcher, which points to Linux kernel service routines. When the return address is popped off the stack, returns to the next instruction. The instruction is called the interrupt return, or IRET, which completes the execution of program flow. Take some time and look at the entire table of system calls by opening up a terminal and typing cat/user/include/asm/unistd_32.h. Below is a snapshot of just a few of them. As you can see, the exit 1 represents the sys_exit that we utilized in our above code. Starting with this lesson, we will take a 3-step approach. Step 1, program. Step 2, debug. And step 3, hack. Each week, we will start with a program like you see here. The following week, we will take it into GDB and examine what exactly is going on at the assembly level. And finally, in the third series of each week, we will hack the data in GDB to change it to whatever we want, demonstrating the ability to control program flow, which includes learning how to hack malware to a point where it is not a threat. We will not necessarily look at malware directly, as I would rather focus on the topics of assembly language programs that will give you the tools and understanding so that any program can be debugged and manipulated to your liking. That is the purpose of these tutorials. The information you will learn in this tutorial series can be used with high-level GUI debuggers like IDA Pro as well. However, I will focus only on the GNU GDB debugger. I look forward to seeing you all next week when we dive into creating our first assembly debug. Part 23, ASM Debugging 1, Moving Immediate Data. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's begin by loading the binary into GDB. To load into GDB, type gdb-q moving underscore immediate underscore data. Let's first set a breakpoint on start by typing b underscore starts. We can then run the program by typing R. To then begin disassembly, we simply type disassemble, or the short version DISAS. We coded a NOP, which means no operation, or 0x90 from an opcode perspective for proper debugging purposes, which the breakpoint properly hit. This is good practice when creating assembly programs. The native syntax, as I have stated many times before, is AT&T syntax, which you see above. I painfully go back and forth deliberately so that you have comfort in each. However, going forward, I will be sticking to the AT&T syntax. However, wanted to show you a few examples of both. I will state again that if you ever want to see Intel syntax, simply type set-disassembly-flavor Intel, and you will have what you are looking for. We first use the command SI, which means step into, to advance to the next instruction. What we see here at underscore start plus 0 is you are moving the hex value of 0x64 into EAX. This is simply moving decimal 100, or as the computer sees it, hex 0x64 into EAX, which demonstrates moving an immediate value into a register. We step again and then use the command IR, which, keep in mind, has a space between them to give us information on the state of the CPU registers. We can see EAX now has the value of 0x64 hex, or 100 decimal. After we step into again and do a disassemble, we see that we have then moved the value of 0x50 into the buffer label, as can refer back to the source code from last week to see. When dealing with non-registered data, we can use the print command above as we type print /x buffer, and it clearly shows us that the value inside buffer is 0x50. The /x designation means show us the value in hex. Consequently, you can review slide 2 of this tutorial above. You see at underscore start plus 5, the immediate value of 0x50 loaded into the buffer label, or in this case, the address of buffer, which is 0x80 490 90, and we can examine it by using the examine instruction by typing x/xb followed by 0x80 490 90, which shows us 1 hex byte at that location, which yields 0x50. We will be doing this with every program example so that we can dive into the debugging process. If there are any questions, please leave them below in the comments. I look forward to seeing you all next week when we dive into creating our first assembly hack. Part 24, ASM Hacking 1, Moving Immediate Data. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's begin by loading the binary into GDB. To load into GDB, we type gdb-q followed by the name of the file, which is moving_immediate_data. Let's first set a breakpoint on start by typing b_start. We can then run the program by typing R. To then begin disassembly, we simply type disassemble. We coded a NOP, which means no operation, or 0x90 from an opcode perspective for proper debugging purposes, which the breakpoint properly hits. This is good practice when creating assembly programs. Let's have some fun. At this point, let's step into once and do an IR to see that 0x64 has in fact been moved into EAX. We can see EAX has the value of 0x64 or 100 decimal. Let's hack that value now by setting EAX to say something like 0x66 by typing set $EAX equals 0x66. Bam, there we go. You can see the ultimate power of assembly right here. We just hacked the value from 0x64 to 0x66, or 100 to 102 decimal. This is a trivial example. However, you can clearly see when you learn to master these concepts, you develop a greater power over the computer. With each program that we create, we will have a very simple lesson like this where we will hijack at least one portion of the code so we can not only see how the program is created and debugged, but how we can manipulate it to whatever we want. I look forward to seeing you all next week when we dive into creating our second assembly program. Part 25, ASM Program 2, Moving Data Between Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. In our second program, we will demonstrate how we can move data between registers. Moving data from one register to another is the fastest way to move data. It is always advisable to keep data between registers as much as can be engineered for speed. Specifically, we will move the value in EDX into EAX. We will initialize this program with a simple immediate value of 22 decimal, which will go into EDX and ultimately into EAX. Keep in mind you can only move similar registers between each other. We know that EAX and EDX are 32-bit registers. We know that each of these registers can be accessed by their 16-bit values as AX and DX respectively. You can't move a 32-bit value into a 16-bit value and vice versa. I look forward to seeing you all next week when we dive into debugging our second assembly program. Part 26, ASM Debugging 2, Moving Data Between Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's debug the second program below. Now, I'm going to have to take a pause here just to fill in a few gaps so that the person following this does not get confused. We have a section here that you are going to have to copy in your text editor of choice. However, the author of this PDF is not telling you because apparently he is expecting you to, at this point, know what you're doing and be able to follow along with his methodology, so he is leaving out a few things. You basically want to copy the text on this screen using your text editor of choice, Nano or Vim, such as what is being used in this PDF, and you are going to want to give it the naming convention that we originally learned how to use in Part 22. So if I open up my terminal emulator, I have a file inside of this directory that is called moving data between registers .s, and this is the methodology and naming convention that was shown to us in Part 22. So this file right here, once you copy this data in your text editor, the name of the actual file should be moving underscore data underscore between underscore registers .s. And then when you have that, before we can move on to this part of the text in the lower portion of the screen where we fire up GDB and set the breakpoint, we first have to run a few commands, which once again we learned in Part 22. We have to do AS-32-O for the output file, and we're going to name the output file moving underscore data underscore between underscore registers .o, and the file that we are using is that file ending in .s. The next command that I run is ld-m elf underscore i386 -o for output file. The name of the file, which is going to be our executable, is going to be moving underscore data underscore between underscore registers with no dot or no dot extension at the end. And the file that we are running this command on is the file we created in the previous command that ends in .o. And I put ls instead of ld, and there we go. So now you see that we have a file that ends in .s, we have the file that ends in .o, and now we have our actual executable right here that we are going to then use for the remainder of this very brief tutorial. Now, let's debug the second program below. Let's fire up GDB and break on underscore starts, run the binary, and disassemble. Now, once again, small deviation from what we see in the PDF. It says, now let's step twice or step into twice and then run the command I space R. However, you do not actually see them step into this twice from the pictures in the PDF. So go ahead and step into once, step into twice, and then run the command I space R. And you can see that this matches what you see on the screenshots in the PDF in the background. As we can see, the value of 0x16 or 22 decimal did move into EDX successfully. If I go back over to the screen, you can see that this is accurate to what we just did. Now we are going to step into again, which you do not see them do in the PDF, and then run IR again. As you can see, we have successfully moved EDX into EAX. I look forward to seeing you all next week when we dive into hacking our second assembly program. Part 27, ASM Hacking 2, Moving Data Between Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's hack the second program below. Let's fire up GDB and break on underscore start, run the binary, and disassemble. Now let's step into twice and run IR. As we can see, the value of 0x16 or 22 in decimal did move into EDX successfully. This is what we did in the last lesson. However, here we are going to hack that value to something else. Here is the value, which is 22, which we did do in the last lesson. We can set the EDX register to something like 0x19, for example, by running set $EDX equals 0x19. I space R. As you can see, we easily hack the value of EDX to 0x19 or 25 in decimal. Hopefully you see some very simple patterns now that we are diving into very simple assembly language programs. The key is to understand how to manipulate values and instructions so that you have complete control over the binary. We are going to continue to move at a snail's pace throughout the rest of this tutorial, as my goal is to give everyone very small bite-sized examples of how to understand x86 assembly. I look forward to seeing you all next week when we dive into writing our third assembly program. Part 28, ASM Program 3, Moving Data Between Memory and Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. In our third program, we will demonstrate how we can move data between memory and registers. I am going to use Vim to create and open up a file that will be called moving_data_between_memory_registers.s. I for insert mode, and I am going to type verbatim what you see in the screenshots from the text. Okay, specifically, we will move the value of inside the constant integer of 10 decimal into ECX. Keep in mind, to assemble, we type the following command: AS-32-O moving_data_between_memory_and_registers.O, followed by the name of the file we just created, which is moving_data_between_memory_and_registers.s. To link the object file, we type ld-m elf_i386 followed by -o for output file, and we are going to provide the name of moving underscore data underscore between underscore memory underscore and underscore registers with no dot or anything after for the name of our executable, followed by the name of the file we created in the previous command, which is ending in .o. I look forward to seeing you all next week when we dive into debugging our third assembly program. Part 29, ASM Debugging 3, Moving Data Between Memory and Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's debug. Specifically, we will move the value inside the constant integer of 10 decimal into ECX. We open GDB in quiet mode and break on _start and run the following commands above. As we can see, when we info registers, the value of ECX is 0. After we step into it twice, we now see the value of ECX as 10 decimal of 0xa hex. Here is the previous value of ECX, which we can see is 0. After stepping into it twice and running IR with a space in between, we see now that ECX has the value of decimal 10. I look forward to seeing you all next week when we dive into hacking our third assembly program. Part 30, ASM Hacking 3, Moving Data Between Memory and Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's hack. Specifically, we will move the value inside the constant integer of 10 decimal into ECX like before. We open GDB in quiet mode and break on _start and run the following commands above. As we can see, when we info registers, the value of ECX is 0. Let's do a step into and another step into. And here is the value of ECX, which is currently 0. So I will step into once, and I will step into twice. IR. As you can see, the value of ECX is 10 decimal, or 0xa hex, as it was in the prior lesson. Now let's hack that value to something else. I'll run the command set $ECX equals 1337. And we will do an I space R. And we can see that the value of ECX is now 1337, or 0x539 in hex. As you can clearly see, we hacked the value of ECX to 0x539 hex, or 1337 in decimal. As I have stated throughout this series, each of these lessons are very bite-sized examples, so you get the hard muscle memory on how to hack through a variety of situations so that you ultimately have a complete mastery of processor control. I look forward to seeing you all next week when we dive into creating our 4th assembly program. Part 31, ASM Program 4, Moving Data Between Registers and Memory. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. In our 4th program, we will demonstrate how we can move data between registers and memory. This is not to be confused with previous lessons where we were moving data between memory and registers. So first I'm going to have to create this file that we see the text for on the screen, and I will do so by using Vim to create and open a file that will be called moving_data_between_registers_and_memory.s. I for insert mode, and now I will type out what we see on the screen. Specifically, we will move the immediate value of 777 in decimal into EAX. We then move that value stored in EAX into the constant value in memory, which initially had the value of 10 decimal at runtime. Keep in mind, we could have called the value anything. However, I called it constant as it was set up as a constant in the .data section. You can clearly see it can be manipulated, so it is not a constant. I chose constant deliberately, as if it was in pure form, the value would stay 10 decimal or 0xa in hex. This code is purely an academic exercise, as variable data normally would be set up under the .bss section. However, I wanted to demonstrate that the above is possible to show the absolute flexibility of assembly language. Keep in mind, to assemble, we type the following command. To link the object file, we type this command. I look forward to seeing you all next week when we dive into debugging our 4th assembly program. Part 32, ASM Debugging 4, Moving Data Between Registers and Memory. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. In our 4th program, we will demonstrate how we can move data between registers and memory. Specifically, we will move the immediate value of 777 in decimal into EAX. We then move that value stored in EAX into the constant value in memory, which initially had the value of 10 decimal at runtime. Keep in mind, we could have called the value anything. However, I called it constant as it was set up as a constant in the .data section. So let's go ahead and run GDB in quiet mode. Going to set a breakpoint on _start. Run. Step into once, step into twice, and step into a third time. As you can see above, we go into GDB and clearly see that the value of constant has been replaced with 777 decimal, where in the code it was clearly set at 10 decimal in line 6 of the code at the beginning of this tutorial. We can clearly see that in line 16 of the code, the value of 777 decimal was successfully moved into EAX and into the memory value of constants. I look forward to seeing you all next week when we dive into hacking our 4th assembly program. Part 33. ASM Hacking 4, Moving Data Between Registers and Memory. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's re-examine the source code. We again can see above that we will move the immediate value of 777 decimal into EAX. We then move that value stored in EAX into the constant value in memory, which initially had the value of 10 decimal at runtime. Keep in mind, we could have called the value anything. However, I called it constant as it was set up as a constant in the .data section. So I have fired up GDB, and I am going to break on start, run, step into once, step into twice, step into a third time. As you can see above, we go into GDB and clearly see that the value of constant has been replaced with 777 decimal, where in the code it was clearly set at 10 decimal in line 6 of the code at the beginning of this tutorial. We can clearly see that in line 16 of the code, the value of 777 decimal was successfully moved into EAX and into the memory value of constant. Now, if I go back over to GDB, I did actually have a few issues with this. And one is that if you just try to follow along with the PDF and type in the command print followed by constant, you are going to get something similar to what you see on the screen here. Constant has unknown type, cast it to its declared type. So maybe this is a little outdated in the PDF, and an updated version of GDB, you don't do it that way. I'm not really sure, but I know just through trial and error that if you want to actually print out the constant, you're going to have to include a $ before constant. However, I still get back a different result than that which I see in the PDF. So I get back that 1 is void. I do not get back the value of 777. But whatever is going on here, I'm not going to let that hold me up from continuing to move forward in the PDF and more importantly to continue to learn from the PDF. So if I go back over to the PDF, we will just continue forward, and now let's hack this thing. I am going to go back to GDB, and I'm going to attempt to set the constant to a value of 666. Once again, I get that same message back. It does not let me set the constant, so I'm going to rerun that command, and this time I'm going to put a $ in front of constant. And that time it did work. Now if I attempt to print out the value of constant again, I do get back that the value is 666, and we are just going to continue forward. We took the very same steps as we did the last time with the debugging lesson. Here we hack the value of constant, to which we hack the value from 777 to 666. I look forward to seeing you all next week when we dive into creating our 5th assembly program. Part 34, ASM Program 5, Indirect Addressing with Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. In our 5th program, we will demonstrate how we can manipulate indirect addressing with registers. I'm going to open up my terminal emulator, and using Vim is my text editor. I am going to create and open a file using the same naming convention that we have been using in previous lessons. So the first file that I will create to store all of this text for this assembly program is going to end in .s. So using Vim, I will create a file, indirect underscore addressing underscore with underscore registers .s. I for insert mode. And now let's go ahead and type out this assembly program. We can place more than one value in memory as indicated above. In the past, our memory location contained one single value. In the above, as you can see, the value of constants contains 11 separate values. This creates a sequential series of data values placed in memory. Each data value occupies 1 unit of memory, which is an integer of 4 bytes. We must use an index system to determine these values, as what we have created above is an array. We will utilize the indexed memory mode, where the memory address is determined by a base address, an offset address to add to the base address, and the size of the data element, in our case an integer of 4 bytes, and an indexed to determine which data element to select. Keep in mind, an array starts with index 0. Therefore, in the above code, we see 1 moving into EDI, which is the second index, which ultimately goes into EBX. We will dive deeper into this in the next lesson we debug. However, I want you to take some time to study the code above and get a good grasp of what is going on. Keep in mind, to assemble, we type AS-32-O for the output file, and the name of the output file is going to be indirect underscore addressing underscore with underscore registers.o, and the file that we are running this command on, our argument is going to be indirect underscore addressing underscore with underscore registers dot s. To link the object file, we type ld-m elf underscore i386-o for the output file, and the file is going to be indirect underscore addressing underscore with underscore registers, and the file that we are running this on is going to be indirect underscore addressing underscore with underscore registers dot o. I look forward to seeing you all next week when we dive into debugging our 5th assembly program. Part 35, ASM Debugging 5, Indirect Addressing with Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. In our 5th program, we demonstrated how we can manipulate indirect addressing with registers. I want to start by addressing the question of why I use AT&T syntax. In previous lessons, I provided many ways to easily convert back and forth between AT&T syntax and Intel syntax. I deliberately choose this path so that it forces you to be comfortable with the most complex flavor of x86. If you are confused with this syntax, please review the prior lessons as I go through the differences between both. Let's recap. We will use objdump to take a compiled binary such as the one above that we compiled in our last lesson and show how we can view its Intel source code. So I'm going to run the command objdump -d -M Intel, and the binary that we are running this on is indirect addressing with registers, and we are going to pipe the output of that into grep, grepping for the main function, which is start, and we're going to do -A followed by 24 to show the 24 lines after the main function, which is start. Now back to our regularly scheduled program. Let's load the binary into GDB and break on _start. Step a few steps and examine 6 of the 11 values inside the constants label. We then move the memory address of the constants label into EDI and move the immediate value of 25 decimal into the second index of our array. This is in essence a source code hack, as we are changing the original value of 8 to 25. If you examine the source code, you see line 18 where we load the value of 1 into EDI. Keep in mind this is the second value, as arrays are 0 based. You can see we changed the value of 8 decimal into 25 as explained. This is our first introduction to arrays in assembly language. It is critical that you understand how they work, as you may someday be a malware analyst or reverse engineer looking at the compiled binary of any number of higher level program compiled arrays. In our next lesson, we will manually hack one of these values in GDB. Keep in mind, we will have to overwrite the contents inside an actual memory address with an immediate value. The fun is only beginning. I look forward to seeing you all next week when we dive into hacking our 5th assembly program. Part 36, ASM Hacking 5. indirect addressing with registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's re-examine the source once more. Let's once again load the binary into GDB and break on the _start main function. I'm going to run. As we look above, we see the command print *0x804909E. We see that it yields a value of 5 decimal. The binary at runtime puts the values inside the constants label to a respective memory address. Now I'm going to pause here because this is where it can really start to get confusing, and that is because when you go to do this on your machine, most likely you're not going to have this same address. The address is going to be different on your machine, and if I go back to GDB, paste that in, hit enter, you see that we get back 0. And that's because when I ran this, it's using different memory locations, and I need to figure out what those are. So one of the things that I can do to do that is if I go back up in the PDF here, you see in the previous chapter we ran this command inside of GDB, and that gave us some information back on the starting points of the memory locations for the array. So if I go back to GDB and I type SI to step into, and then disassemble SI again to step into, and I will do x/6 ampersand constants. And this, once again, this will most likely be different when you do this on your machine, but when you do this, this gives you an idea of the memory location for your array. And if I utilize this value right here, for example, which is in hexadecimal, going back to the PDF, instead of trying to print the value at that memory location, I will print the value at the memory location that I grabbed from right here. And you see that I get back the value of 5, which is the first value in this array. And that's going to be the example that I'm going to use and build off of. So if we go back to the PDF, once again, going back to the text, the binary at runtime puts the values inside the constants label to a respective memory address. In this case, we see that the pointer to this hexadecimal value, or this hexadecimal value with the asterisk in front, holds 5 decimal, as we have stated above. An integer holds 4 bytes of data. The next value in our array will be stored at this hexadecimal address. This memory location will hold the value of 8. If we were to continue to advance through the array, we would move 4 bytes to the next value and so forth. Remember, each memory location in x86 32-bit assembly holds 4 bytes of data. Let's hack. I am going to quit this session of GDB. I am going to start again. GDB-Q indirect underscore addressing underscore with underscore registers. I'm going to break on underscore start. And run. And I'm going to type the command x/6d ampersand constants. Now I am going to utilize what will be the memory space for the first value in this array, which is 5. This memory space address in hexadecimal will most likely be different on your system. Keep that in mind. I'm going to copy that, and I'm going to run the command set asterisk, paste in that hexadecimal memory address, and equals sign, and 66. Now if I rerun that previous command, x/6d ampersand constants, we see that I have changed the value of 5 to 66. So going back to the text, after we broke on underscore start and ran, we examined the array like we did in our prior lesson. Here we hacked the value at this hexadecimal address to 66 decimal instead of 8 decimal, and we can see that we successfully changed one element of the array. This lesson is very important to understand how arrays are ultimately stored in memory and how to manipulate and hack them. If you have any questions, please leave them in the comments below. I look forward to seeing you all next week when we dive into programming our 6th assembly program. Part 37, ASM program number 6, CMOV instructions. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. In our 6th program, we will demonstrate how we can work with CMOV instructions. Before we dive into some code, let's talk about CMOV and what it is. CMOV can prevent the processor from utilizing the jump instructions and speeds up the respective binary. There are unsigned CMOV instructions such as CMOVA or CMOVNBE. There are also signed CMOV instructions such as CMOVGE or CMOVNL. Keep in mind to review the relationships between the unsigned and signed operations. The unsigned instructions utilize the CF, ZF, and PF to determine the difference between the two operands, where the signed instructions utilize the SF and the OF to indicate the condition of the comparison between the operands. If you need a refresher on the flags, please review Part 14 on flags in this series. The CMOV instructions rely on a mathematical instruction that sets the E flags register to operate and therefore saves the programmer to use jump statements after the compare statement. Let's examine some source code. Okay, let's begin with lines 21 and 22. This is nothing new that we have experienced, as we are simply moving the array into EBX. On line 24, we see the find underscore smallest value function, to where we are cycling through the array and using the CMOVB to find the lowest value ultimately. We see CMP, %sign EBX, comma, %sign EAX, to which CMP, or compare, subtracts the first operand from the second and sets the E flags register appropriately. At this point, the CMOVB is used to replace the value in EBX with the value in EAX if the value is smaller than what was originally in the EBX register. After we exit the loop, we see three sets of sys_rights to first display our message, second to display our converted integer to ASCII value, and then finally a period and line feed. Keep in mind, to assemble, we type AS-32-O CMOV_instructions.O followed by CMOV_instructions.S. To link the object file, we type LD-M elf_I386-O CMOV_instructions followed by CMOV_instructions.O. I look forward to seeing you all next week when we dive into debugging our 6th assembly program. Part 38, ASM debugging number 6, CMOV instructions. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's re-examine some source code. Let's break on this hexadecimal address, which is line 31. Let's do a R to run and then type print $EBX, and we can see the value of 7. Now, in reality, when you go to do this for yourself, you are not necessarily going to be able to follow along with this verbatim and say, for example, copy and paste this hexadecimal address, because most likely the address space is going to appear different on your system. So I'm going to give you a very layman's methodology of still being able to follow along and learn something from this documentation. I'm going to go to my terminal emulator, and here is the binary CMOV_instructions. going to start GDB in quiet mode. And the first thing that I am going to do is, even though it does not call for this in the PDF, I'm going to set a breakpoint on our main function, which is _start. And we know that that is our main function because we are able to actually look at the original program written in assembly language. So we know that _start is our main function. Now I'm going to do that simply because I then want, after setting the breakpoint, I then want to be able to run the program and then disassemble and take a look at what the memory space looks like in hexadecimal over here. So I will actually step into once, and I'm going to step into twice, and then I'm going to step in a third time. And once I see this string pop up, find _smallest value, I then disassemble again. And now I'm able to easily look at the hexadecimal addresses in memory space over here on the left hand side, and if I go back to the PDF, they were setting a breakpoint at this address, which is line 31. If I come up here and look at line 31 is converting an integer into ASCII. So we have our opcode on the left, ADDL, and you can see that we have the value of 0x30 and we have our register EBX. If I go back to the disassembled dump in GDB, we can actually locate that simply by process of elimination. And if we look at this line right here, this seems to line up with what we are looking for. So I will copy this value and I will add, there probably is a better approach to this, but as I am just a novice learning this and figuring this out on my own, this was how I was able to rationalize what I was doing and still follow along with the PDF. So now that I have that value, I am going to quit and restart GDB. And this time I'm going to set a breakpoint at that specific address. Hit enter, run the program, and print $EBX, and we get back the value of 7. So essentially this was a way for me to still follow along with the PDF and be at the same point that they are at in the PDF. Okay, now let's break on this hexadecimal address, which is line 46. Remember, when we are examining the value of answer, it has been converted to its ASCII printable equivalent. So in order to see the value of 7, you would type x/1c ampersand answer. Okay, so what I am going to do to find that hexadecimal value, because once again it is going to be different for me on my system, I am going to do another dump of the assembler code, and I'm going to actually take a look and just see if I am able to locate that. Okay, so in order for me to locate this value, which is line 46 in the PDF, if we go back up here and look at line 46, we have an opcode of move with an L, M-O-V-L. We have an integer of 4, and we have a register that is EAX. So if I go back to my dump, I'm looking for something with the move opcode, and I'm looking for the EAX register, and it had an integer of 4 in it. So I am going to make the assumption that it is either this line right here or it is this line right here. And for purposes of just better understanding what's going on and learning, I really don't think it matters that much which one you look at here. The whole idea is to just kind of understand what you're doing and how to manipulate some of these values in these registers. So I am just going to pick this one right here, and I am going to copy that value, and we are going to set another breakpoint on that hexadecimal address. So I have breakpoint 2 that has been set. I'm going to single step with S, and then I will type out x/1c ampersand answer. As we can see, it has been converted to its ASCII printable equivalent, and I feel like that is satisfactory in getting what was meant to be received from this PDF in this lesson. So with that being said, I look forward to seeing you all next week when we dive into hacking our 6th assembly program. Part 39, ASM hacking number 6, CMOV instructions. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Let's bring the binary into GDB. Let's now run the binary. We see that the smallest value is 7, which is expected. Our final bit of instruction in this tutorial will teach you how to jump to any part of the execution that you so choose. We set the EIP register to a specific hexadecimal address, which is the exit routine. We see now that it bypasses all of the code from the NOP instruction when we broke on _start. You now can use this command to jump anywhere inside of any binary within the debugger. I'm starting GDB in quiet mode. I'm setting a breakpoint on _start. I'm running the binary. I will do a disassemble. I'm going to step into once, I'm going to step into again, and I'm going to step into a third time, and then do a single step. And we see that the smallest value is 7. And this also allows me to get what for me on my system when running this binary is going to be the hexadecimal address space related to the exit routine. So I will copy that. This will be different for you. And I am going to run the program. I'll do Y for yes. And I'm going to set the EIP register to the value of that exit routine. Now I will single step, and we can see that it bypassed all of the code from the NOP instruction, and we were able to jump to a completely different part within this binary. I look forward to seeing all of you next week when we wrap up our tutorial series. Part 40, Conclusion. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. This has been an extensive and hopefully beneficial tutorial series for you all. Understanding assembly language is so important to everyone when trying to understand how malware works, in addition to programming no matter bare metal assembly, C, C++, or even Java, Python, or iOS or Android development. If you are looking to pursue a career in reverse engineering, assembly will be second nature to you. Most of us will pursue higher level language development, as computers and devices are significantly more powerful today, which allows for rapid development languages. I want to thank you all for joining me on this tutorial series and look forward to you all making an impact in the future of tomorrow. That will include the reading of Reversing for Everyone until we start it up again. And when we do start it up again, we'll be delving into the 32-bit ARM architecture. My name is Mr. Fresh, and thank you for joining me on this journey.